Hi, and welcome to Chapter 2, Structure of the Atom for your Radiologic Technology Physics course. Now, why do we care so much about the structure of the atom? That is because everything that is even remotely related to X-rays includes or is happening because of things at the atomic level. So interactions in the X-ray tube that produce X-rays occur at the atomic level. For example, hopefully, you remember from last semester in imaging, you learned a little bit about the X-ray tube that I'm outlining right here. And hopefully, you also remember that in there is like literally nothing. It is a vacuum. It's a vacuum tube. So there are no air atoms in there that we would usually find, like oxygen, for example. Nothing is in there. What that means is the electrons produced at the cathode here can shoot on over to the anode without hitting anything else. They'll come over here, interact with the anode, and give us the X-rays we need. If it weren't a vacuum and there were atoms in the air here inside this, instead of shooting on over and hitting the anode, these would interact with all those atoms that you can't see, right? But they're there, all of those instead of just the anode. You might think of it as maybe you went to an archery range, maybe you're trying to learn the bow and to handle the bow and the arrow, and in front of your target is a forest of trees, making it much harder for you to just try and get over and hit the target. Not very efficient that way. So interactions between the X-ray photons and the human body also occur at the atomic level. What we're going to see is, for example, when an X-ray photon encounters a bone atom, for example, calcium, it's more likely to undergo the photoelectric effect. So it's from an understanding of atoms that we understand then what kind of effects will occur and what ultimately we will get as an X-ray, for example. So the atoms in bone differ from those in air, and thus we get something that looks different on an X-ray. X-ray photons exiting the patient also interact at the atomic level with the image receptor. Atoms are specifically chosen in the image receptor for the X-ray system. Now, in class and on your own, please take a look at this link. It takes you to the periodic table that shows you what atoms look like for each of those little things on the periodic table. So, what you'll see is that if you click on this, there will be a little thing on the side here that's going to show you there's a nucleus, and it's the center of the atom, made up of protons and neutrons. The protons are positively charged, the neutrons are neutral, and they're held together in the center of the atom. Now, orbiting them, just like maybe the planets orbit the sun, you might think, the planets need to stay exactly where they are, orbiting the sun. If they get even a little closer or a little further away, it can have catastrophic effects on the temperature of that planet and, everything that goes with that. So it's just like that for an atom. Orbiting that nucleus are electrons in defined energy levels and distances from that nucleus. And another thing about an atom, I kind of like this little thing here, but they are in everything. And because of that, electrical charge becomes a characteristic of matter. It's a part of, just atoms in general, which means it's a part of matter because atoms make up everything. So if something has atoms in it, and everything does, except for, I guess, that vacuum tube, but then it can carry an electric charge. All right. So even inside your body, everything is made up of atoms, and atoms are where electrical charges begin. All right. Now, I do want to take just a second, and you might notice that we're looking at an MRI image here. Now, MRI is possible because of atoms and because an electric charge is possible within the human body. Not only that, but also magnetic properties. Because as you're going to see as our conversations throughout the semester continue, wherever you can find electricity, you're going to be able to find magnetism. And that's why it's called electromagnetic energy. So MRI depends heavily on hydrogen atoms in the body. It turns them into little magnets for a very brief moment, to make it kind of like a basic explanation. And we get our image here from a magnetic resonance imaging machine. All right, so if an atom has an equal number of protons and protons and electrons, it has no net charge. It's neutral here, right? Not happy, not sad, nothing. All right, so if the negative charges start to outweigh the positives, the atom is called a negative ion. What this means is it's lost protons, maybe, or gained too many electrons. And now the net charge on that atom is negative. If you have the opposite going on and the positive charges, or those protons, outnumber the electrons, the negatives, the atom is called a positive ion. So keep that in mind. And when you have an ion, it means that it is not quite stable. And therefore, it will interact with its surroundings to try and make itself stable again. Well, we'll get more into that later. More about the nucleus. So remember I said, we're having these conversations kind of about the atom and electricity. And remember when I said where you have electricity, you kind of have magnetism? Magnets are easier to use for analogies to kind of get the concepts of electricity, and they kind of just go hand in hand. So that's why you're going to sometimes see magnets all of a sudden just show up. So the nucleus is held together by a strong nuclear force that creates a binding energy. A binding energy creates a strong attraction in the nucleus, overcoming the natural tendency for like charges to repel. So why I bring up these magnets is that what you're going to see is that two of the same side, so you're trying to stick a positive to a positive or negative to a negative, the sides here, they're going to try and repel each other. So I don't know if you've ever done that experiment with magnets where you sorry, I keep trying to restart this video, where you try to push two of the same sides together and they won't go together. In fact, they repel each other like you're seeing here. Well, you might be thinking about an atom and thinking, well, you have a lot of positive charges pushed all together there in that nucleus, right? All those protons. Well, they're held together by a strong nuclear force. They hold the protons and neutrons together to form the nucleus. Now, the amount of attraction that that nucleus has, keeping it all together, represents the amount of energy you would need to then separate them. Now, in addition to nuclear binding energy, you also have electron binding energy. Now, electrons orbit the nucleus at very high velocities. This video is moving kind of slowly, but here we see the protons and neutrons held together, and then you have electrons orbiting. Now, just like in magnets, right? The negative electrons here and the positive protons here are going to want to attract each other, right? So you might be thinking, well, why don't the electrons just fly into the nucleus to meet the protons like we saw in this video here, right? Now we have a North Pole and a South Pole, and they're going to click together. Well, the electrons are held in their orbits by electron binding energy, and they also have a centrifugal or centripetal force happening. Because of their velocity and their rotation around the nucleus, they have just this set of energies that makes it possible for them to exactly rotate around the nucleus at those defined levels and not slam into the nucleus and not fly away. You have a pull here and a push, a pull and a push created that allows you the electrons to continue orbiting. Now, the electron binding energy depends on the following. It's how close the electron is to the nucleus. So the closer it is, just like we saw in this video, right? The closer it gets, the stronger it gets. The further away you get from, the other magnet, and you have these two opposing ends to each other. Further away you get, the weaker the attraction will get until it lets go. But the closer you get, the stronger that attraction is. Same thing for electrons. The closer they are to this nucleus, the stronger their electron binding energy is. And also how many protons are, having an effect on that electron will depend on that. All right, so nuclear binding energy and electron binding energy are key determinants of X-ray production. The two types of atomic interactions that produce X-rays are characteristic and Bremsstrahlung. So later on, we're going to learn about how, because of those binding energies, basically how much energy we have to use with X-rays if we want to hit one of these guys out of there. We have to have a very specific energy level that matches what's happening in this atom to get that electron out and create an X-ray. All right, so an atom has defined energy levels, right? Here's our tungsten atom. Here's an atom we might find in bone. It's calcium there. And you can see it's much different than our hydrogen atom here with just one electron. So each of these, right, each one's going to have a K shell. The K shell is the closest one. So it's going to have the strongest binding energy, right? How close the electron is to the nucleus? Well, the closest atom is going to be the one in this K shell, this first shell here, and it's going to have the strongest energy. As the shells go out, their electron binding energy gets a little weaker, just like we saw with these magnets. The further away it gets, the weaker it gets. Keep doing that. Okay. And remember, it's a three-dimensional orbit. On paper, in the book, it's all 2D, but if you click on that link right here, it's going to take you somewhere where you can mess around a little bit with the atom and see it more 3D-ish to remember that they are orbiting 3D. Same with this one. Just trying to give you an idea. All right, so each electron shell is lettered to begin with K, and that's what we were talking about in that previous slide. This first shell here is the K shell, and it just goes out alphabetically from there. So this would be K, L, M, N, O, P would be the outermost shell. And Q, it's up to Q. Atoms can go up to that shell. All right, so the shells fill from K outward. And what's important to remember is the outermost shells may not fill completely. For example, here, right? There's only two in this outermost shell. That's fine. They don't have to fill completely. They could, well, we'll talk about that in a minute. So each cell does have a limit to the number of electrons that it can hold. That limit can be determined with the formula 2n squared, in which n is the shell's number. So, for example, in this atom right here, let me bring up my writing tool. This is the K shell, right? And it's going to have a number 1. So N for the K shell would equal number 1. Here's going to be the L shell, and it's going to have number 2. N for the L shell is going to be 2. HIJKLM. So here's the M shell, and it's going to be number 3. So the N, this N right here for the M shell is going to be number 3. And so on. Let me erase all the, oh, let me erase these. All right. Now, and you can find out the limit with that formula. So let's say, let me bring these back up again. Let's say I want to figure out what the limit is for the M shell right here. It's the third shell is the number 3. So I'm going to go 2 times 3 squared. Well, 3 squared is 9. So 9 times 2 is 18. All right. So it's saying that M shell can have 18 in it max. If this atom needs 19 electrons by the time it gets here to this M shell, then it's going to have to put 1 electron up here in the N shell, and so on. So, for example, our tungsten atom here, it needed the 2 extra electrons here, so it pushed them out. Darn. It pushed them out all the way to this P shell, so it could have 2 in that P shell. Erase this. All right, let's keep going. Now, the outer shell limit can be determined with that formula. Excuse me, sorry. But the outermost shell can hold a maximum of 8. So we have our little exception here. And I showed you an octopus because they have 8 legs, right? So it's fine that there's 2 here. They could technically be one in that P shell right there, but there cannot be more than 8. Now, roll fast, right? Ready? Technically, there it is. The P shell, okay, if this 1, 2, 3, 4, 5, 6. So let's calculate how many can be in the P shell. 2 times 6 squared, sorry, not very good handwriting with the mouse. 6 times 6, 36 times 2 is 72, right? So the P shell could have 72, but if it's the outermost shell, if it's the last shell that an atom has, it can no longer have 72. It's not allowed. The outermost shell can hold a maximum of 8. So it's fine that there are only 2 in here, but if this is the outer shell here, this P shell, it could not have more than 8. Now, if this needed more, it's going to have to add another shell, keep adding, and so on to make sure it fits those rules. All right, atoms represent targets for interaction. So here's our X-ray again, right? Well, our electron, let's say, coming off the cathode. Here it comes. They're going to shoot it at a tungsten atom in the anode. Well, the more complex the atom, the greater the opportunity for interaction. So, say you have a target and you're trying to hit this, and that's the only thing you can hit to get points. Now, let's say you're trying to learn to shoot a bow and arrow. Now, this is your target. Any one of these that you hit, you're going to get points for. It'd be much easier to score points at some point, especially as a beginner, let's say, here than on this one. So that's one of the many reasons that tungsten is chosen for atoms. Okay, so classification and bonding. Atomic number it can be represented as Z, and it is the number of protons an atom contains in its nucleus. If it's a stable atom, meaning that it's neutral, right? Remember this, right? It's going to have an equal number of protons and electrons. There's no net charge. It's neutral. It's not radioactive or desperate to gain or lose an electron to make it stable, and so on. This atomic number here, protons, actually also equals the amount of electrons it has too. An atom contains, 74. So atomic mass number is the number of protons and neutrons an atom has in its nucleus. It's here. And elements are the simplest forms of substances that can compose matter. So back to atomic mass number can be represented as A, while atomic number can be Z. And it's important to just remember what atomic number versus atomic mass number mean. Okay, a molecule is two or more atoms bonded together. Compound is a combination of elements bonded. The chemical symbol is an abbreviation of the element. Here we saw W is the abbreviation for tungsten. Isotopes. You have the same number of protons, but a different number of neutrons. And this is why we care about them, specifically this one. So if you are interested in something maybe going into nuclear medicine or maybe radiation therapy, something like that, there are stable isotopes and radioactive ones like iodine-131. These can serve as tracers, power sources, tools. We have radioactivity. So as soon as we start kind of messing around with the stable atomic nature of certain atoms, we can make them radioactive. And that's useful in radiation-related fields. So ionic bonding. Based on the attraction of opposing charges, one atom gives up an electron and one atom takes an electron. So remember how we were talking about electrons wanting to be stable? They want to have a no net charge. They want to be neutral, right? They just want to be. As soon as we start to mess with that, we can start to create bonding. So for example, here, see how this became negative because it gained more negatives than it had positives. So it became a net negative charge. Well, because this one lost an electron to this atom, it now became positive because now, without as many electrons, it has more positives outweighing the negatives. Well, okay. Well, now I have a positive and a negative, and just like magnets, they're going to want to snap together. So they might do what we call an ionic bonding. And if you'll recall from the very beginning, see which one it is. I think it was, we talked about ions. When one atom gives up, I can't find the slide, but if an atom gives up an electron and one atom gains electrons, they can be referred to as ions. So anyway, that's why we have ionic bonding. You're going to see that word ion. Same thing with like ionization. You're kind of talking about messing around with the electrons a little bit there. All right. We also have something called covalent bonding. And this you might want to think about, cooperating, that sort of thing. But an outermost electron from one just begins to orbit the nucleus of another, and ends up as kind of a figure eight pattern. And that's just another type of bonding. And that is it. Sorry about the length of this video, but hopefully it was helpful.